about the movement of water, which is always passive, right? So it's diffusion. It's water moving along its own concentration gradient. And this was unaffected by the membrane potential. Okay, so the polarity of charge across the cells did not influence the movement of water. And if you look at the scenario here, very similar to the one we drew on Friday. There are two scenarios. The first cell shows that there is a higher solute concentration inside the cell, and outside the cell there are no solutes, so this is pure water. Okay, and so we have a gradient where there is a higher concentration of solute, a lower or zero concentration of solute, and so water wants to move along its concentration gradient where it is highest on the outside and lowest on the inside. The second scenario is the opposite. So we have lots more solute particles dissolved in this solution, and there is less solute dissolved inside the cell. And so the gradient created for water is in the opposite direction, where it wants to move from the inside of the cell to the outside of the cell. All right, so this is an example of what osmosis is, the movement of water according to the concentration gradient. That brings us to talk about osmolarity. And this is a representation of the total solute concentration in a solution. Okay, I want you to bear this in mind because we're going to differentiate it from tonicity, which is slightly different. Okay, so osmolarity, is really the total amount of solutes that are displaced or dissociated in your solution of water. When we define osmolarity, we speak about the mole versus the osmole. The mole versus the osmole. And the mole is really the solute particles before they are dissolved in our water. So if you have 1 mole of glucose, right, and we dissolve it into 1 liter of water, the osmolarity of that solution would be 0.1 osmole. Alternatively, if we have the same amount, 1 mole of sodium chloride, and we dissociate that into the same amount of water, 1 liter, the osmolarity of that solution will be different. It will be 0.2 osmoles, and that is because sodium and chloride will further dissociate into separate particles. So the osmolarity is really taking into consideration all of the individual particles in that solution. So because sodium will dissociate into 0.1 osmole of sodium and 0.1 osmole of chloride, the combined osmolarity will be 0.2 osmole. Okay, whereas glucose will remain 0.1 osmole. Then we speak about the milliosmole, and this is specifically for body fluid composition. Okay, when we speak about the osmolarity of extracellular fluid, of intracellular fluid, we use the milliosmole because we're speaking in fractions of an osmole. Okay, 1/1000th of an osmole, and so we use milliosmole specifically for body fluids. And so the standard osmolarity of our intracellular fluid and our extracellular fluid is 300 milliosmoles per liter of water. And all that means is that there are 300 moles of particle dissolved in 1 liter of our body fluid. And that's osmolarity. Let's look at some examples here. Now again, when we speak about osmolarity, we're looking at all the dissolved solutes in that solution. So a solution, or let's take, for example, we have 3 cells here, and they're all suspended in the extracellular fluid. And we have 3 descriptions of osmolarity. So in the first scenario, we have a hyperosmotic solution, and this creates a gradient where water wants to move out of the cell simply because there's more solute in that solution outside the cell. Right? There's more solute outside the cell, hence there's a gradient where water wants to diffuse out of the cell, and what we get is shrinkage or shriveling of the cell. Okay. In the second scenario in the middle, there is no net movement of water. So we still have movement of water in and out, but there's no net accumulation such that the cell volume would change. And that's because the osmolarity of the extracellular fluid is the same as the osmolarity of the internal fluid of the cell. Okay, so there's no net movement in this second scenario. In the third scenario, let's say hypoosmotic solution. This is hypoosmotic, and water is going to move in the opposite direction. It's going to move inside the cell, again, because now we have less solute, less particles dissolved in the extracellular fluid, right? More water, and so water wants to go from where it's at a high concentration into the cell where it's at a lower concentration. Okay, and that will eventually cause swelling of the cell and eventually lysis. Now, lysis means to rupture or to burst, and that's the effect of hypoosmotic solutions. Now, ideally in the body, we want to create an environment where the solution, the extracellular fluid, is isoosmotic in relationship to the intracellular fluid. We don't want our cells to be shriveling up the way they do in a hyperosmotic solution, or to swell until they rupture the way they do in a hypoosmotic solution. So ideally what we want is to keep this diffusional equilibrium where fluid is moving, but there's no net accumulation on either side. And in fact, there are many disease states. So for example, there's a state of water intoxication, which is where excess water moves into your cells. That can cause vomiting, that can cause comas, and eventually death. And the reverse is true as well. If you have severe dehydration, excess water moves out of your cells eventually shrivel up. That can also lead to death. Okay, that can be fatal. All right. Let's speak about osmotic pressure. Osmotic pressure. And this is really a representation of the amount of solute concentration, but it's represented as a force, right? Or as a pull. Okay, so let's say, for example, we have these two scenarios, side 1 and side 2. Right, in side 1, we have a higher concentration of water and a lower concentration of solutes dissolved in that water. On side 2, we have the opposite. We have a higher concentration of solutes, a lower concentration of water. And so side 2, having more solutes, creates this pull where it wants to draw water from side 1. And that pull is osmotic pressure. Okay. So it's a reflection, or it's an expression of the amount of solutes dissolved in concentration, and it's expressed as a pull or as a force, okay? And that's your osmotic pressure. So eventually, water is going to be pulled from this side, side 1, over to side 2. And if we look at the osmotic pressures here, now it's sometimes represented in atmospheres, sometimes in millimeters of mercury. Here it's represented in atmospheres. And you can see that on side 1, there are less solutes, hence a smaller osmotic pressure, 7.4. Whereas on side 2, there are more solutes, hence a greater osmotic pressure. And again, this is the side that has the stronger pull. So water is going to move from side 1, where there's less of an osmotic pressure, over to side 2, where there's a stronger force pulling it. Okay, and this is osmotic pressure, this ability to pull water to the side that has the greater solute concentration. All right, any questions on that? Okay. It can also be expressed as the pressure that would be applied to stop the movement of water, right? What is the pressure that that water is exerting, and what pressure would be needed to stop that movement of water? Okay. All right, so now we're going to speak about tonicity. And tonicity is very similar to osmolarity, but it's quite different, right? It's the water gradient across a membrane, but it's only taking into consideration the impermeable solutes. The osmolarity took all the solids into consideration. Tonicity is only taking into consideration the impermeable solutes, that is, the solutes that cannot move across that membrane. Okay? And we'll talk about an example shortly, but tonicity really speaks about what effect does this solution have on the cell? Does it shrink, right? Does it swell? Does it lyse? What is the physical effect of the solution on the cell? That's your tonicity. It can be isotonic in the middle here. And isotonic means that the solution had no physical change on the cell. The cell volume did not change. So if your extracellular fluid is 300 milliosmoles, your intracellular fluid is 300 milliosmoles, this is said to be an isotonic solution because it doesn't change the cell volume of this cell. It neither shrinks nor lyses. Okay. If we look at a hypotonic solution, right, that is going to increase the flux of water into the cell, and the cell will swell. Okay, this is said to be hypotonic. On the other hand, we have hypertonic, where water will move out of the cell and the cell will shrink. So really looking at the effect of the solution on water is what will describe or define the tonicity. Okay, now, we said that osmolarity and tonicity are different, and we'll use this example to sort of illustrate those differences. So a solution can be initially isoosmotic. Just to go back here and redefine what osmolarity is, right? Isoosmotic meaning that the extracellular fluid is the same osmolarity as the intracellular fluid. Okay, so let's jump back here. This fluid on the left side, it starts out being isoosmotic. So what we have is there's a solute that's dissolved in the intracellular fluid, and that's going to give us an osmolarity of 300 milliosmoles. In the extracellular fluid, there's a different solute. So there's urea in the extracellular fluid. Now you want to bear in mind that this membrane is not permeable to the solute inside, right? That solute in purple. So the osmolarity, as I mentioned before, is going to take all the solutes into consideration, whether the membrane is permeable to them or not. Okay, so we have an equal osmolarity across this membrane, and so we say that this solution is isoosmotic. Okay. Let's look at scenario B, right? Same scenario, but what we notice is there is now, over time, a movement of the urea into the cell. And that's because the membrane is permeable to urea, but not permeable to the solute in purple. So urea now moves into the cell, and that increases the osmolarity inside the cell. So now we have a higher osmolarity inside the cell, reflected by more particles, and a lower osmolarity outside the cell. Now we have a gradient where water wants to move. Okay, so water wants to move from an area where it's higher in concentration into the cell where it's lower in concentration. Okay. Can everyone see that? Same scenario. And over time, because that urea now moves into the cell, we have a change in the concentration gradient. So now we have a gradient where water can move. Water is going to move from an area where it's highest in concentration now, outside the cell, into the cell. So that cell will begin to do what? It will begin to swell. As water moves into the cell, it begins to swell. Now, based upon what we said about tonicity, is this still an isotonic solution? If the cell is swelling, is this an isotonic solution? It's not, right? It's not. As long as we have shrinkage or swelling, it's not an isotonic solution, but it can be an isoosmotic solution. Okay, that's the driving point here. The tonicity takes into account only the solutes that are impermeable to this membrane. So if you look at it that way, in this scenario here, you can completely ignore urea. And if you ignored urea, there would be more solute inside the cell and no solute outside the cell, and so you would have a gradient. Right? So the tonicity is taking only the impermeable solutes into account, whereas the osmolarity takes all the solutes into account. Okay? So a solution can be isoosmotic, but not isotonic. Alrighty, that's very important. Okay, so in actuality, this solution is hypotonic, although it began as an isoosmotic solution. All right, this table sort of summarizes some of those differences. And again, the main takeaway here is that osmolarity takes both the permeable and impermeable solids into consideration, whereas tonicity is only looking at the permeable solids. That's what the word impermeant means. Okay? How many of those solids are impermeable to that membrane? All right, so you don't want to really memorize this table, but do use it to help you understand those terms and to help you understand those examples we just talked about. All right, and again, we're just summarizing that difference here. So again, we're speaking about tonicity here. The images on the top of the screen, so A, are showing us a hypotonic solution. So on the left-hand side, we have 300, an osmolarity of 300 inside the cell, and osmolarity of 150 outside the cell. So this creates a gradient where water wants to do what? Where will water move in this first scenario? Will it move in or out of the cell? So where will water want to move in the image at the top? It's going to want to move in, right? We have more solute dissolved inside the cell, and so water is going to move according to its concentration gradient from outside the cell inside the cell. And it's going to do so to the extent to which it is required to equalize the osmolarity. So if we have 300 inside the cell, in order to equalize the osmolarity, we're going to have to move 300 inside the cell, all right? I'm sorry, another 150 inside the cell, and so those become equal. Alrighty? So this is hypotonic. At the bottom, right, is an alternative scenario. This is a hypertonic solution. So we have an osmolarity of 600 outside the cell and 300 inside the cell. And so what water wants to do is move from the inside of the cell to the outside of the cell.